Okay. So this is determining empirical formulas. An empirical formula gives, by definition, the lowest whole number ratio of atoms in a compound. Okay. So what this means is that every ionic compound is an empirical formula. I don't know if you remember back from when we did, ionic compounds, but we did things like this. We took magnesium with a +2 charge and oxygen with a -2 charge. And you may have learned the crisscross method. And I might have had people that wrote Mg2O2. And I said, no, you can't write that. You gotta make this MgO. Okay. That's because every ionic compound is an empirical formula. It is the lowest whole number ratio of atoms in the compound. So NaCl is an empirical formula and K2SO4 is an empirical formula, and that just kind of automatically happens. Now, as far as molecular compounds go, they may or may not be empirical formulas. CO2 happens to be an empirical formula. That's the lowest whole number ratio. But I want you to look down here at these examples. N2O4 is not an empirical formula, all right? Its empirical formula is NO2, right? That's the lowest whole number ratio between N2O4. C6H12O6, glucose, really important. It's in photosynthesis. You should have heard about it before. It is not an empirical formula. It's what we call a molecular formula. Its empirical formula is a 1 to 2 to 1 ratio. Got it? So why do we do these? Well, we're going to use those percentages that we used before to figure out empirical formulas. And then from there, if we're feeling saucy, we can get to molecular formulas. So how do you calculate an empirical formula? It's actually pretty easy. You need to think about what a formula is. A formula is a ratio of atoms. Again, NaCl does not mean it's 50% sodium and 50% chlorine by mass, but it does mean that there's a 1-to-1 ratio between sodium and chlorine. So the empirical formula tells me the ratio of atoms in the compound. All right. We also call this the mole ratio of the elements. So if you take something like, I don't know, like how about magnesium chloride? What that tells me is that there are 2 chlorine atoms for every 1 magnesium. So the mole ratio is a 2-to-1 ratio of chlorine to magnesium, right? So this is how we do it. And because I don't give you a textbook, I make you kind of convert these amounts of elements into moles without showing you in some textbook examples. So this is calculating empirical formula. Step number 1, convert the amounts of elements into moles. It's no help to you to work with something in grams. We've established that all atoms have a different mass, so that ratio doesn't work for you. The second step is to find the mole ratio. Mathematically, we do this by dividing all numbers by the lowest number of moles. All right. Let me show you what that means so you're not confused. If I look at the number 6 and the number 3, and I say, hey guys, what's the ratio between 6 and 3? A lot of you would be like, no problem. The ratio is 2 to 1. Okay. Because you've passed math classes. You're not in, 5th grade anymore. But what you did mathematically in your head very quickly was you divided 6 by 3 and you divided 3 by 3. And you had 6 divided by 3 equals 2 and 3 divided by 3 equals 1. So that's how you got this final answer of 2 to 1 ratio. All right. So when we're doing that, that's why we're doing that. And then step number 3, which we won't get to today, but you might get to the next time we meet. If necessary, you need to use multiple ratios, multiple numbers or multiples to get to whole numbers. And the reason that we need whole numbers is because, guys, you never see You see CH4 or something like that. You never see C1.8 H4.82. That's not a very good chemical formula. They're always whole number ratios. Okay, so this says find the empirical formula of a compound that contains 10.4 grams of phosphorus and 35.7 grams of chlorine. So step number one, convert to moles, right? I can't look at that. What some students will do right away is they'll look at that and they'll say, okay, well, it's 10 and it's 35.7. So like maybe it's a 1:3 ratio or a 1:4 ratio. No. You're not allowed to look at it like that because all atoms have a different mass. So the first thing you've got to do is convert it to moles. So convert phosphorus to moles, convert chlorine to moles. I'm using the periodic table, right? Grams cancel, and I'm left with these 2 mole values. Now is when I'm looking at the ratio between the moles. The ratio between the grams means nothing to me. It's the ratio between the moles that's important. So you might be able to look at that and see the whole number ratio without going through the math. But I like to go through the math anyway, right? We've got 0.335. So this is where you divide by the lowest number. Right? So I end up with, and again, I'm looking for whole numbers. 1, looking for a whole number here. I'm not looking for decimals. Decimals don't help me at all. 3. Okay, now even if it came out to 2.97 or 3.01, it's close enough to 3 for me that I can make the conclusion that this right here, this compound is PCl3. There's 1 phosphorus to every 3 chlorines. And again, that's taking something theoretical and turning it to something for real. Okay, so again, we converted this ratio. I divided by the lowest whole number ratio. We got phosphorus to chlorine is a 1:3 ratio, which gave me the empirical formula. Let me give you another example. Let's say we're now not going into the lab. Now I'm giving you a percent composition, which is what we were working with before. Well, if I give you a percent composition, you can't convert a percent to moles, but you can convert grams to moles. So you're going to assume 100 grams of the compound, and you're then going to convert to moles and find the molar ratio like you did before. So in an example like this, if I say give the formula of a compound made up of 43% sodium, 11.3% carbon, and 45.3% oxygen, I can just convert this, guys, grams, and grams. I can pretend in my head I'm working with 100 grams of that so that I can work with moles. So here's this problem. I just want to give myself more space to write. It says, give the formula of a compound made up of that, right? So I've got to start by converting to moles first. So 43.4 grams into moles. So this is sodium. It has a mass of 22.99 grams per 1 mole. The next one is carbon, 11.3 grams. This is 12.01 grams per 1 mole. And this is oxygen, 45.3 grams. And I know that the molar mass of that is 16 grams per 1 mole. All right, so I need my calculator, assuming this works. Cool. 43.4 divided by 22.99. So I get, again, You don't have to worry about specifics. Call this 1.88, call it 1.89, call it whatever you want, because again, we're looking for kind of whole numbers here. For once in your chemistry life, you don't have to worry about having the perfect amount here. This one is about 0.94-ish, and oops, 45.3. Oh, goodness gracious. 45.3 divided by 16 gives me 2.83, right? So that's my moles. Now you may be able to look at that and see the molar ratio. You're looking for a molar ratio, a whole number molar ratio at that point. Or you might have to divide it. And if you have to divide it, that's okay. You divide by the lowest one. So divided by 0.94, divided by 0.94, divided by 0.94. And guess what? This comes out to be 1, all right, or about 1. This one comes out to be 3 or about 3. And this one comes out to be 2 or about 2, which is going to give me a final formula of 2 NAs, Na2. I've only got 1 C, and I've got 3 oxygens, which you guys should recognize as sodium carbonate. Okay, so let's go back here. So there's one more step. At the beginning, I told you there was empirical formulas, and those are the lowest whole number ratio, but then I admitted to the dreaded molecular formula. So C6H12O6 is a molecular formula. If the empirical formula gives the lowest whole number ratio, that might not actually be the molecular formula. So you can look at these formulas right here, and you can think to yourself, all right, what do these have in common? We've got CH2, C2H4, C3H6, C4H8. These all have the same empirical formula, right? They're all CH2. They're all a 2-to-1 ratio. And if you look at their masses, look, their mass is double, triple, quadruple. So you can use those masses to figure out this one is 4 times as large as the empirical formula. This one is 3 times as large. This one is 2 times as large. And this one is the empirical formula. So that's how you move from empirical formulas to molecular formulas. And we're not going to do that today, but it's something you should be able to do after just a little tiny bit of practice.